Welcome to this explainer. Today, we're exploring the awe-inspiring and, honestly, mostly hidden engineering behind modern offshore drilling. We're going to look at exactly how engineers manage to defy physics, gravity, and literal miles of solid rock to extract the resources that keep our world running.
Think about this for just a second. How do you steer a drill bit that's attached to miles of solid steel pipe, navigating through dense rock kilometers beneath the ocean floor, when you can't even see it? I mean, it sounds completely like science fiction, right? But it's an absolute daily reality in modern engineering.
Well, let's dive right into it. For the longest time, people thought drilling just meant going straight down. But in reality, wells actually curve. We don't just drill vertically anymore. We can gradually change the trajectory of a wellbore to hit targets that are kilometers away horizontally from where we started on the surface.
So here is our roadmap for today. First, the power of directional drilling. Second, bending the wellbore. Third, horizontal wells and productivity. Fourth, geosteering. And finally, extended reach drilling.
All right, Section 1. The power of directional drilling, one platform, many targets. To really understand the engineering here, you first got to understand the massive economic problem it solves. Building a brand new billion-dollar offshore platform directly over every single isolated pocket of oil? Yeah, that's just financially impossible. So the solution is steering the well. A single fixed platform can basically act like a giant hub, deploying what look like robotic tentacles deep underground. A really skilled directional drilling team can reach and drain a reservoir area of 5 to 10 square kilometers, or sometimes even more. So instead of needing a separate platform over every single well location, one platform does the whole shebang. This drastically lowers development costs and, of course, minimizes the environmental footprint on the ocean's surface.
Moving on to Section 2, bending the wellbore, the mechanics of steering.
Okay, so how exactly does a literal solid steel drill string change its trajectory deep underground? Let's cleanly break down the vocabulary of a directional well profile. Step 1 is the build section. This is where you start vertical and then gradually increase your inclination, basically angling away from the vertical. Step 2 is the tangent section. That's where you hold that specific angle and compass direction, drilling in a straight, angled line toward your target. And then step 3, if you need it, is the drop section, where you gently reduce that inclination back toward vertical to hit the target dead on. To actually make those precise turns, engineers use a steerable drilling motor with a bent sub-assembly. And that is literally just a piece of pipe with a super slight 1 to 3 degree bend in it. Now, when you want to steer, you stop rotating the whole drill string from the surface. Instead, you pump drilling mud down the pipe, and that mud powers a turbine motor located just above the bit. So the drill bit spins, but the pipe above it stays completely still. We call this sliding mode. And because of that little bent piece, the bit naturally follows the direction of the bend. Then, when you want to drill straight again, you just switch to rotary mode. You do that by rotating the entire drill string from the top, which essentially carves out a slightly larger straight hole. Pretty clever, right?
But wait, how do they actually know which way the bit is pointing down there? Well, that brings us to MUT pulse telemetry. The downhole tools use accelerometers and magnetometers to measure the exact angle and compass direction. But the absolute genius part is how they get that data back up to the surface. They convert the data into binary code, and then they transmit it by creating pressure signals in the fluid. It's basically like a Morse code of pressure waves traveling all the way back up to the surface, right through the drilling mud itself.
All right, Section 3, horizontal wells and productivity, staying in the zone.
So directional drilling solved one massive problem, but we still had an issue. Vertical wells often barely touch these thin, horizontal oil reservoirs. Just imagine a reservoir that is incredibly wide, but maybe only 10 or 20 meters thick. If you drill straight down, you only get 10 or 20 meters of exposure to the actual oil. The ingenious solution here was taking directional drilling to its logical extreme, turning the drill bit a full 90 degrees so it stays entirely within that horizontal oil layer. Suddenly, instead of 20 meters, you have hundreds or even thousands of meters of payload zone exposed to the wellbore.
The really crucial point here is the impact this has. By turning sideways and staying inside that productive rock, the productivity of a horizontal well can increase by a massive 5 to 10 times compared to a traditional vertical well in the exact same thin reservoir. I mean, that is an absolute game changer for field economics.
Which leads us to Section 4, geosteering, navigating the dark. Now, you might have realized there is a massive critical blind spot here. You're trying to drill horizontally through a super thin 10-meter layer of rock, but you are miles away and you literally can't see a thing.
On top of that, the sandstone isn't perfectly flat, right? It dips and rises constantly. Without real-time data, conventional drilling just relies on pre-planned paths, and if that rock dips unexpectedly, you'll just drill straight out of the top or bottom of the oil-bearing sand and right into worthless shale. That is a very, very costly failure. But with geosteering, you use real-time formation data to actively navigate the bit and stay beautifully centered right in the pay zone. So how in the world is that even possible? Well, sensors placed right behind the drill bit use gamma rays and electromagnetic resistivity to actually see the rock. These sensors can literally look up and see the high gamma ray signatures of shale approaching and then look down to see the clean sand. It's wild. The geologists and the directional driller work together like a pilot and co-pilot. They interpret these logs in real time, constantly steering the bit up or down to ride those geological boundaries absolutely perfectly.
And finally, Section 5. Extended reach drilling, pushing the limits.
This is where we escalate to the absolute ultimate extreme of modern subsurface engineering. Extended reach drilling, or ERD, pushes directional steering limits to targets that are 10, 12, or honestly even 15 kilometers horizontally from the surface location. I want you to try and frame this unseen scale in your mind for a second. It is essentially an underground moonshot. The drill bit is traveling almost 10 miles sideways from the rig before it even reaches its target. But as you'd expect, physics fights back aggressively. As the drill string's inclination increases, gravity is no longer your friend. It no longer helps slide the pipe into the hole. Instead, that massive steel drill string just rests heavily on the low side of the borehole, and friction suddenly becomes the dominant force. You're facing massive drag resisting any forward movement and severe torque resisting rotation. If you exceed the drill string's torque or tensile limits, well, it can cause a catastrophic twist-off, which is where the steel pipe literally snaps in torsion, or worse, a pull-apart.
Now, to prevent these catastrophic, totally project-ruining disasters, it requires some seriously meticulous bleeding-edge engineering. Literally everything has to be optimized. Managing torque and drag in ERD wells means the drilling mud is chemically engineered to be incredibly slippery to reduce that friction. The bottom hole assembly is perfectly balanced, and drillers use continuous, real-time data to delicately adjust their weight and rotational parameters. They have to stay just within the ultimate physical limits of the steel without breaking it.
Which brings us to a final thought. We've seen how engineers can steer a drill bit 15 kilometers completely sideways, relying on nothing but magnetic fields, gamma rays, and Morse code pressure waves sent through mud. It is just an awe-inspiring technological leap. So, it really leaves you wondering, as we continue to push the boundaries of materials and robotics even further, what exactly is the next impossible frontier for subsurface engineering? Thank you for joining me on this explainer. I hope you found it as fascinating as I do.